greats of physics, it's still a hypothetical subject. It gets closer to reality through observations of the center of our galaxy, stars whipping around in a manner that could only really be explained by there being a black hole in the center of our galaxy, but it's still indirect. To actually have a direct image that you can look at, what a beautiful arc, narrative arc from the theoretical to the absolutely established. And that's what we hope will happen with other areas, for instance, string theory, right? I mean, wholly mathematical subject at the outset and still pretty much a wholly mathematical subject today. Yeah, do we long for that image where we can look at it and say, string, it's real, you know, I mean, how thrilling to be part of that journey, to be part of that step that moves things from the abstract to the concrete.
Yeah, so like the image of the DNA, the early images of DNA,
Sure.
for example. But there is something special. So the problem with strings is they're tiny. So it's harder to take a picture. In the following sense, when you think of a black hole, when you have a swirl of, I guess, what is, I don't even know, it's dust, or whatever, light.
Accreting onto the event horizon.
And then there's darkness.
Yeah.
And you just imagine, so that picture in particular, I guess, is of a gigantic black hole. So you just, I mean, it's terrifying.
Billions of times the mass of the sun.
Yeah, so it's both exciting and terrifying. I mean, I don't know where you fall on the spectrum. I think it's exciting at first. Like, the longer I think about it, every time I think about it, the more terrifying it becomes. So it always starts exciting, and then it goes to terrifying. And both are feelings, very human feelings that I appreciate. It's like terrified awe. Somehow is still beautiful.
That's a good way of saying it. And I think I kind of share that reaction, because there is a way in which, when you work on this subject, like all the time, I teach about black holes, write the equations on the blackboard. The ideas reside in a very cognitive, I don't know, mathematical portion of the brain, or at least for me. And it's only when you like sit down and it's quiet and you start to contemplate, wait, this isn't just like a mathematical game. There are these monsters out there. Now, I don't, not in a sense of I fear for my life, but it's a sense of how extraordinary is this universe. And so it is breathtaking.
How powerful nature is.
Yeah, how stupendously powerful nature is. And so there is a deep sense of humility that I think this instills if you really allow the ideas to sink in.
Well, I have to ask about the most stupendously powerful thing to have ever happened in our universe, which is the Big Bang.
Yes.
What's up with the Big Bang? So we can, I mean, with gravitational waves, the hope is, when you have more and more accurate measurements of the gravitational waves, you can crawl back further and further back in time towards the Big Bang. Do you have a hope that we'll be able to understand the early spark that created our universe?
Yeah. You know, that and the deep interior of a black hole are, I think, the biggest mysteries that we hope the melding of quantum mechanics and gravity will reveal, will illuminate. And, you know, what question could be more captivating than why is there something rather than nothing, right? Why is there a universe at all? And will the theories that we're developing take us to an answer to that? I don't know. Even if we truly knew what the Big Bang is, and that's a big question in its own right, one would still be left with the question, well, okay, so you've explained the process by which a tiny nugget of a universe, a tiny nugget of space-time, can undergo some kind of growth to yield the world around us. But presumably in that explanation, you're going to involve mathematics and some ingredients like quantum fields or matter or energy or something. Where did that stuff come from? You know, can we get to that level of explanation? I don't know, but it is remarkable that if you ask what happened a millionth of a second after the Big Bang, it's not really that controversial any longer, right? Even though there's a lot of argument in the field, and it's very heated right now, I should say, regarding what is the right theory of the Big Bang? What is the right theory of early universe cosmology? Where I mean early, much earlier than a millionth of a second. A lot of dissent, a lot of heated arguments about that.
No pun intended.
Yeah, right, exactly. But you go like a millionth of a second after that, and we're on pretty firm ground. Isn't that amazing? Right?
Yeah.
To understand, what happened from that point forward. But to go back is controversial. So there is this theory called inflationary cosmology, which I would say has been the dominant paradigm since early 1980s. So what does that mean? Roughly 40 years now, it's been the dominant cosmological paradigm. And it makes use of a curious feature of Einstein's general theory of relativity, his theory of gravity, where Einstein shows us mathematically that gravity can not only be attractive, the kind of gravity that we're used to, things pulled together, but it can also be repulsive. And that fact is then leveraged by people like Alan Guth and Andre Linde, and at the time Paul Steinhardt and Andreas Albrecht and others, to say, okay, if we had a little nugget in the earlier universe which was filled with the stuff that yields this repulsive gravity, well, that would have blown everything apart. It would cause everything to swell. Beautiful explanation for what the bang in the Big Bang was. And then people mathematically analyze the consequences of this idea, and they make predictions for tiny temperature differences across the night sky that in principle could be measured. You send up balloons, you send up satellites with very refined thermometers, and they measure the temperature of the night sky, and the statistical distribution of the temperature differences agrees with the mathematical predictions. I mean,
It's amazing.
you just sort of have to stand in awe of this insight. So you think, aha, the theory has been established. But scientists are an incredibly skeptical bunch. And some scientists, including one of the people who helped develop the theory at the outset, Paul Steinhardt, comes along and says, well, yeah, this theory's done pretty well so far, but there are aspects of this theory that are making me lose confidence. For instance, this theory seems to suggest that there might be other universes. Like, how do you make sense of a theory that suggests there are other universes? Or there are others who come along and say this theory seems to talk about length scales that are minuscule even by the so-called Planck length, the sort of shortest length that we can imagine making sense of in a theory of quantum gravity. How do you make sense of that? And so on and so forth. They develop a list of things that they consider to be chinks in the inflationary cosmological theory's armor. And they develop other ideas which they claim yield the same prediction as inflationary cosmology for those temperature differences across space, but don't suffer from these problems. And then the inflationary cosmology folks say, no, hang on. Your theory suffers from different problems. And so the argument goes, it's a healthy debate. Talk about real debates in science. So when you ask, what's up with the Big Bang? I don't know right now. If you would have asked me 5 years ago, maybe even less than that, 3 or 4 years ago, I would have said, look, inflationary cosmology has some issues. But the package of explanations it provides is so potent, and the issues that beset it are seemingly solvable to me, that I would imagine it's going to, in the end, win out. I would still say that today, but I wouldn't say it as loudly. I wouldn't say it as confidently. I think it's worth thinking about alternate ideas, and it could be the case that the paradigm at some point shifts.
Does dark matter and dark energy fit into the shifting of the explanations for those?
Yeah, certainly. So dark energy has, in the inflationary theory, is kind of a big mystery. So dark energy is the observational realization in the last 20 years that not only is the universe expanding, it's expanding ever more quickly. Something is still pushing things outward. And the explanation is that there's like a residual version of the repulsive gravity from the early universe, but it's such a strange number. When you write that amount of dark energy using the relevant units in a theory of quantum gravity, it's a decimal point followed by like 120 zeros and then a 1. We're not used to those kinds of numbers in physics. We're used to a half, 1 pi e